All right, I guess we can start. Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Georgia Chalvatzaki, who is an assistant professor and research leader at the Intelligent Robotic Systems for Assistance Group, IROSA, at TU Darmstadt in Germany. So something about her, she received her diploma and PhD in electrical and computer engineering at the National Technical University of Athens in Greece. And her research interests lie in the intersection of classical robotics and machine learning. And the aim is to develop behaviors for enabling mobile manipulator robots to solve complex tasks in domestic environments where you have human-in-the-loop situations. And I guess a nice example is the one we see in this first slide here. So she holds a Emmy Noether grant for AI methods from the German Research Foundation, and also she was voted the AI newcomer in 2021 by the German Information Society, which is very cool. The title of today's talk is Shaping Robotic Assistance Through Structured Robot Learning, and is an extended version of the recent keynote talk she gave at IROS. I'm personally very excited to hear more about the topic, and that's why I give you the stage, Georgia. Go ahead.
Thank you very much for the very kind introduction, and thank you for inviting me. I'm very excited to talk to your group. And as we discussed before, I will ask you if you have questions while I am progressing, because maybe you will find like topics that are not you may seem that they are disconnected, but I will convince you that they are all connected under the umbrella of structured robot learning. So yeah, my group is called IROSA. I am working for robotic assistance, and my motivation, what got me into robotics, it was when I was around 5-6 years old, and in the weekend we would watch the Jetsons that would have also Rosie the robot, a mobile manipulator, a robotic assistant that would do all the household tasks, would deliver the food to the Jetson family and so on. So the vision was to have such a robot like this Tiago robot that is delivering me this pair in this case. So what is the main issue now is like, how can we enable such robots to leave the structured lab environments and enter the real world that it is unstructured and requires safe also interaction with humans and the overall environment. And I will walk you through 5 points where we will see that we can actually employ structure in order to scale robotic behavior such that we can have robots that can perform potentially, hopefully, tasks like Rosie the robot. But of course, growing up, I understood that, okay, it's not about just having Rosie the robot in my home, doing my house, fixing my household. There are more pressing events, right? So yeah, to take like a bit of perspective, the journalists have been reporting shortage of healthcare workers in many developed countries around the world that show a shocking extent of staffing crisis that effectively threaten the effective health coverage. So it is clear that there is something missing here, and it's not only about the hospitals. If we see at some data, we will see that the aging population is constantly rising. So the people aged 60 years old or over have reached 1 billion and they keep increasing. Now, on the other hand, we have COVID-19. And additionally, we have now digitalization, the options for working from home, which means that many people opt for other higher paying jobs than taking over the job of a carer, that it is a very stressful and also physically impacting the body's work, and also dangerous in some cases, and which means that the seniors are stuck at home alone. This means only one thing, right? We need robotic assistance. And my vision is that for achieving this long-wished dream of having a robotic assistance, we need to unlock the path to embodied intelligence through mobile manipulation systems. And why do we care about mobile manipulation systems? Well, they combine mobility and manipulability such that they can move around the world and manipulate different objects and execute different tasks. They're equipped with different sensors so that they can perceive the world around them, and they have an increased workspace, as in theory, the whole world is their workspace. And now, as mobile manipulation systems are structured robotic systems, let us unveil what do I mean by structured robot learning or structuring robot learning in general. Now, if we give a definition that I hope you already know, robot learning is the field that uses machine learning methods in robotics to allow robots to acquire skills through imitation and interaction with the environment. Now, in our lab, what we try to do is to take into account the structure of the problem to enable faster, safer, and scalable learning of robot behaviors. And what do we want to achieve in my group with this structured robot learning? Basically, we have three desired properties for our robots, for our mobile manipulation robots. First, coordinated and generalized manipulation skills. Second, fluid and safe human-robot interactions. And finally, scalable long horizon behaviors. And now I will walk you through these 5 research areas in which structure comes into the game and gives us a flavor of this desiderata of robotic behaviors for our robots. Before I go there, I would like to take a look at this interaction scene with me and my robot again. The robot has to perform this handover task. And in order to execute this task, the robot needs to understand the intention of the human. It needs to position itself into the world. It needs to understand how to grasp and deliver an object. And overall, it has to act safely. And let's see now how we can bring structure here into the game. So first, we will see how we can use structure to learn models for effective human-robot interaction, and how, in general, we can use models to learn models for planning and see how we can scale robotic behavior in these cases. We will see how we can deploy scene structure in order to learn long horizon tasks, and how we can extract scene from observations, scene structure from observations. We then will see how we can use the robot structure itself as a prior for learning mobile manipulation. And we will also discuss more generally, how can we learn objectives in order to perform complex manipulation tasks? And we will finally arrive to the major point of safety, where we'll see how we can learn constraints and use them for safe learning of human-robot interaction. Well, we'll see all these points in some different test beds, but I will try to bring it all together and convince you that these are some flavors that we have to achieve in order to scale mobile manipulation. So why robotic assistants in general, apart from Rosie the robot? Another reason was that during my PhD, I was working with robotic assistants in different scenarios. Mainly, I was studying human behavior models for controlling mobility assistant robots, like the one that you see here in the picture with an elderly person that would have different pathologies that would affect their stability and way of walking. So the goal was to actually create control strategies for this robot in order to adapt to the specific needs of its user, and also act proactively in cases of instability, and overall to track the rehabilitation process of the elderly people or any user that would need to use a robotic relator. So one of the contributions during my PhD was basically, I came to realize that people with pathologies, let's say Parkinson's, for example, actually exhibit completely different gait cycle than the normal one. So we had to actually detect the way its specific user walks and adapt a tracking framework that would only take laser points and be able to, in real time, give us information about position, velocities, and also the gait phase. And for that, we developed a structured Markov model that would monitor basically the different gait phases of a human, and would be able to adjust the velocity model that we would use for the underlying particle filter that would track each leg separately, while for the observation, we were using also a probabilistic data association so that we can ensure that, for example, a particle doesn't jump away and track another person that is walking nearby. And this was actually very good because it also allowed us to do real-time inference of the gate phases and also extract parameters that would show us how the rehabilitation process is evolving. And of course, the question was, how can we use this information to actually control the robot, especially if we take also into account the upper body. We were able to study also the stability of the user. I will not go into many details, but if you want, you can ask me and I can tell you how we effectively used camera information and laser tracking to also track the stability of the user. But in general, our problem can be framed as a human-robot coupled navigation scenario in which the robot has always to be in front of the human with some desired orientation and a distance and orientation. And effectively, this should adapt to the specific way of walking. So there are people that are doing like smaller steps, that they are faster or slower. So the robot has to effectively recognize this behavior and adapt accordingly. And we actually have researched different approaches. One approach that we hypothesized that would be very beneficial would be a human-centric model-based reinforcement learning framework, where in this case, we would also deploy a human motion intention model that would predict in a forward horizon the walking intention of the user. And we would use this information in a network that would allow us to learn the basically statistics of this human-robot coupled system in order to extract to sample possible actions for our robot, use them inside a model predictive controller, and take the best action to apply to our robot. And obviously, because we do learning with model-based reinforcement learning, we would aggregate the data and update again this model of human-robot interaction. And we have shown in simulation that this was actually more beneficial than, for example, a kinematic controller, like a leader-follower controller, or pure imitation learning from data that we have gathered from real demonstrations of elderly people working with a robotic rollator. So yeah, in general, the interplay of learning and planning, it is very, very interesting. So as you may know, like if we focus in this part, I hope that you can see my my pointer. This is the standard, let's say, deep reinforcement learning in this particular case framework, where an agent acts on an environment, explores the environment and collects data according to some exploration strategy, use the data to train our favorite DeepRL algorithm that in the case of SAC, this is maximum entropy, so a lot of randomness, which is something that we don't like for our robots. And also that in general, in the end, when you want to learn a complex behavior, you need to acquire a lot of data. So our idea, and actually this was developed concurrently with other approaches like model-based policy optimization, was to use the data that you collect anyways randomly in order to learn a model. And while MBPO approaches would use this model to randomly sample actions, we took a different approach where we said, okay, with this data, we are actually approximating the MDP. We are learning the model, we are learning the reward function, therefore, why not do planning in this approximated MDP? And by doing planning, you can actually also explore locally, taking, let's say, the best possible actions, of course, subject to the fidelity of your model. But also given that we anyways learn a value function with our model-free agent, we can use this value function as the, let's say, end cost in our model predictive control. And this has been realized as an MPPI, basically. Of course, we don't apply any action from this imaginary, let's say, rollouts, but we use the top trajectories to store them in another buffer. We would mix real data with model-based data. And we have shown that this actually improves learning a lot in terms of training time. You can see that our approach that we called MOPAC converges faster to compared to like MBPO, that it was the competitive approach. And we have also used this method to train a robotic hand in the real world from scratch. With all these three agents, soft actor critic, MBPO, and MOPAC. The first task that we show, what we see here is the round valve rotation, where the robot just has to grasp the valve and rotate it till it opens, basically. And as you can see, again, MOPAC learns faster and also more stable behaviors. And then the next task was a bit more challenging because we wanted to basically stress the agent and actually enforce the agent to use all four fingers, because I don't know if you noticed before, the agent understands in all cases that it can actually use only 2 fingers to fulfill this task. So in this task, we perform a finger gating task. This means that the agent is actually has to grasp an apple that is hanging. Keep it lifted so it shouldn't fall down, and rotate it till it reaches a desired orientation. And again, you can see that the other approaches are actually rotating the apple. Sometimes it would fall down, while MOPAC is able to fulfill again the task and is actually exposing some robust behavior. But of course, one problem with model-based reinforcement learning is how can we effectively explore the environment in order to learn a good world model? In the previous case, we were relying on the maximum entropy exploration, but obviously with robotics, this is not always a good option. So in our recent work, we took an active exploration perspective. We got inspired by active inference, and we studied purely model-based reinforcement learning. So we said, like, especially when we have to explore for learning dynamics where the rewards are sparse, it's quite problematic because you don't have a concrete signal of judging whether or not the actions that you're taking and what you represent for your world is actually true. So our approach was actually to alter the model predictive control objective by adding an additional term here that tries to maximize the information gain between some model parameters and the expected states and returns given these parameters if you follow policy pi. And this expected information gain can be seen as a measure of how much the agent expects to learn about the environment by following this policy. And so this, we can imagine that this objective becomes maximum if the agent expects to make observation that will change its belief about the correct choice of model parameters drastically. So this makes the agent, let's say, curious about the environment and tries to explore it, and does this during the rollouts actually that we do through our MPC. And as you can see, we control also the contribution between being goal directed or being, let's say, information seeking with this beta parameter. And again, we have tested this approach initially in simulation. We had this inclined table. The goal is not given as a state, so the state is not goal informed. Therefore, the agent will only get informed about the goal if we obviously reach the goal and we get the maximum reward there. Otherwise, it is only driven by the mutual information objective. And you can see how this agent is able to cover the information. And we were able also to use, again, this same strategy to train this robot from scratch in the real world, simulating more or less the same environment. And we have also tested it with different inclinations of this environment. Does this work? Okay. So yes, and we have also tested it with different inclinations, and in most cases we were able to solve the task. And it was something that we find very encouraging to continue investigating in this direction for model-based reinforcement learning. So yeah, I would maybe see if somebody has a question for this first part in terms of like models, or if I would take like one question now, and if you want, like you have questions later on, I can come back after the end of the talk. If there is no question, I will continue. And we will go to the next part. We will see how we can deploy the scene itself as the scene structure in order to learn long horizon tasks. And as application, let's say test bed in this case, we are going to use what we call assembly discovery. Now, what is assembly discovery? Imagine that you have some architect or designer that gives you some arbitrary design and some building blocks, and they tell you, okay, use these building blocks to fill up the shape. This is actually a project that we have with the architecture department here at TU Darmstadt. So this is obviously a task that requires a long horizon planning, and also it is a combinatorial optimization problem because we need to find the placing sequence of these building blocks to fulfill these arbitrary shapes. You can see like we arbitrarily were sampling some designs in different like areas and some random blocks, and we're trying to basically optimize to fill as much as possible of this design. And we thought that, okay, if we take into account also the scene structure, so these building blocks that we had available, they look like the Tetris blocks, obviously, and we create the scene graph. We can actually build a graph neural network agent that can be trained with reinforcement learning. And we can also deploy the robot into the loop so that we can take into account the feasibility of the robot and whether it can build stable structures and learn actually the task sequencing in this case. So which block should I place where and with what order? And we have also seen that if we deploy search during inference, we can actually generalize pretty well. However, since this is a combinatorial optimization problem, it is actually a very challenging task in terms of exploration. So recently we extended this initial, let's say, end-to-end approach where we train just a GNN reinforcement learning agent into a hierarchical method. In this hierarchy, we have a high-level model-based solution that it is just a mixed integer linear program. It solves the resource assignment. It takes a relaxed version of our problem, so it doesn't consider many of the constraints that are actually there in the physical world. I will explain it a bit more in a while. On the medium level, we have the graph-based reinforcement learning agent that now only explores in the solutions that have been provided by the MIP on the higher level. And on the low level, we have a grasp and motion planning approach where it just transforms the desired assembly commands into robot join motions, because basically this middle agent is actually tells you that, okay, this block has to be placed there. And you just can do planning and actually realize this assembly. So to take a bit more insight for the high level MILP, let's look how this would look like. We have these Tetris-like blocks. We can imagine that our robot has to play 3D Tetris, and we have to fill in this area inside this yellow design. So we voxelize the area, the building area. With pink, we have the voxels that we have to fill, and green are the ones that do not need to be filled because they are outside of the area. So if we see it as a 2D case, we can imagine that in Tetris, usually we have to fulfill a rectangle area, but here we have only the pink area. So we solve a simple mixed integer linear program that in this particular case do not care about structural stability, doesn't consider robot in the loop or task sequencing. So this alleviates the need of constructing some complex and potentially not convex objectives for mixed integer linear programming, but we just do voxel filling. So this effectively gives us a possible set of solutions about which block type we should place where. Now we take this set of solutions And we go to the, let's say, real world. We have the scene graph that represents the blocks that are unplaced, potentially the ones that are already placed, and also the voxels that need to be filled or not, or should remain free. And we do several rounds of message passing in our graph neural network, and with deploying of Q-learning, we can effectively explore actions that were proposed by the MILP. But now in this case, our Q function is basically trained to take into account the structural stability, as this is part of our reward function. Robotic feasibility, as it actually, we have also another term in our reward that checks whether or not the robot is able to execute a collision-free plan and find, let's say, the grasp that will execute the possible assembly action and effectively learns the task sequencing. And we can see that if we just take the heuristic approach of the MILP that doesn't effectively consider the motion execution, it ends up in many collisions. While in our case, effectively, if we also use MCTS planning during inference, we are able to extrapolate into bigger structures, different types of objects being used, and we can also transfer this into the real world for our robot to execute using this digital twin. So here, of course, we use external perception, we initialize our scene, and then open loop, the robot operates the assembly. Luckily, it's able to execute it with not many big problems. And yeah, we found this very interesting in the for the direction of basically task and motion planning, and we are considering how to extend this into different rearrangement tasks. But of course, perception is still a problem. So I will just take a few minutes to show you some cool results that we have in terms of vision-based perception. So how can we, in an unsupervised manner, be able to represent objects in a scene, especially when there are things that come and go, like the hands, or big scenes like here, a human manipulate different objects, too much structure to capture. So recently we have proposed an information theoretic approach for unsupervised key point discovery. So we took inspiration from classical computer vision, and in particular approaches that consider the entropy of the images as a way to represent structure. And we use the entropy in frames in order to enforce key points to actually represent areas that are represented by these masks, and spread the key points in a frame such that they can capture as much as possible of the information that an image carries. But when we are talking about demonstrations or like videos, this is a sequence of frames. So we also introduced a conditional entropy objective that tries to enforce the key point to cover also the new information that is going to come from that it comes from the previous frame to the new frame. And finally, since we want to also temporally learn the dynamics, so the key points to be able to follow the information flow in a video, we also introduced an information transportation loss that would actually enforce the key points to reconstruct the information in a sequence of frames. So we introduced three losses. So as I said, the maximum coverage of the entropy in different frames and their transportation of information as a mutual information objective. And together with some regularizers that would activate or deactivate unnecessary key points if, for example, with a minimum number of key points we can contain information, we were able to, as you can see here, this is our approach, MINT, effectively track objects in dynamic scenes. We can also learn to predict their dynamics. And here you can see some results also from these human demonstrated data sets. And you can see how key points basically disappear when the human hand goes away, or they appear when the human hand is in the scene, or even capture the structure of the scene. And again, this is promising because we can consider this as a low-level representation for also learning from demonstration, like in this simple test bed, but we were able to outperform, for example, CNN-based feature extraction for imitation learning. So yeah, this was the part of exploiting scene. I don't know if there is any question for this part, but I would like to go to the next part that connects to the mobile manipulation finally. Yeah, mobile manipulation in general is very, very difficult. I came to understand this during the last 3 years that I'm here at the Darmstadt, because the robot has to effectively coordinate itself. So where should the base be placed? Where should we activate the arm? What kind of actions we should do, and with, of course, minimum number of actions. So we took a perspective here by considering that the decision-making consider hybrid actions in mobile manipulation. And what do I mean by hybrid actions? We can consider basically the optimal base placement scenario where the robot has to effectively place its body, its base into the world, so the X, Y, and orientation, and also a discrete decision variable on whether or not it should activate the arm to execute a manipulation task. So in order to use this hybrid action space in our favorite deep reinforcement learning approach, we have to form a hybrid policy, in which case we introduced the continuous part and the discrete part, only that the discrete part is actually conditioned on the continuous part. And this effectively makes sense because, I mean, you need to know where you are placed in order to know whether or not you can reach an object. And in order to train this, we had to use a Gumbel softmax reparameterization to allow auto differentiation. And as I said before, this discrete decision variable is connected to the notion of reach. So the agent has to effectively understand if it is able to reach for a target in order to train this decision variable. And for that, we took inspiration from classical approaches in mobile manipulation, that they would consider the operational workspace of the robot. So namely all, let's say, voxelized 6D poses that the agent can reach, and would give you also some frequency of whether or not you can find a solution there. Now, if we take the operational workspace and we consider the floating base scenario, then we can effectively invert this operational workspace and basically cut it on the level of the floor so that we can get the inverse reachability map that looks like this. So for any arbitrary 6D target, we are able to query and invert these maps and cut them on the ground. And you can see that this is, of course, a voxelized approach. It's quite of heuristic. And we thought, what if we actually train an agent on this data set to get a smooth Q-reachability map? So we trained an agent on these local, let's say, reachability tasks, and we acquired this smooth Q-reachability map. However, this is still in the locality of the agent, and mobile manipulation is effectively more long horizon, right? So the agent has to move in the room, approach effectively an object, and, for example, grasp it. And in order to do this, we have to transfer this prior knowledge of the reachability to something longer. And for that, we introduced boosted hybrid reinforcement learning that allows us to do transfer knowledge. And what does it effectively boosting mean? It means that a Q function can be modeled as a sum of residuals. And you start by learning your base, let's say, task, that for us was this smooth Q reachability. And anytime that you need to learn a new task, you add, you learn only the residual. So effectively, you keep the structure of your previous tasks intact, and you only learn the part that is missing for realizing the new task. And we also found that if we add a forward Kullback-Leibler regularization, it gives intrinsic bonuses to the agent. so that it can remember, let's say, good actions from previous tasks. And this framework is also very interesting because it allows us also to handle changing observation spaces and changing reward functions in different tasks. Like, for example, in this case where the AI robot has to reach for an object, this was the original task. Then we transferred into navigating in a large room. Then we added obstacles. Then we wanted to grasp an object, a 6D target. And then again, change the configurations of the training or even find a clearance for grasping an object where other objects on a table are effectively your obstacles. And we were able to transfer this learned reachability map directly in the real world. And here you can see how we can adapt. That's how the agent always adapts to the changes in the environment. We randomly change positions of the table and the agent adapts. And we can use the exact same behavior to execute rearrangement tasks, so pick and placing, because effectively, when you know your reachability, you are able to position yourself and then activate for picking or placing or any task like this. Some failures that we had, it was because when we were training in simulation, so effectively, this reachability agent outputs sub-goals that tells you basically your next base position and whether or not you should activate to pick or play something. And while in simulation, we used our own, let's say, planner. In the real world, we used the ROS navigation stack. So there it was a bit more, let's say, safe and wouldn't allow us to go very close to the table. So we experienced some failures because of that, but this can be effectively changed if you train with the same strategy or if you change, of course, your base planner. So do you have any questions maybe at this point? If there are no questions, then I will continue. So we arrived to the point of objectives. So effectively, we saw now that for the mobile manipulation, we're only considering these basic pick and placing tasks, but manipulation is broader than just pick and placing. And there are tasks that are actually very difficult to learn, and or even specifying some reward function, or they are hard exploration tasks. And you really need human demonstrations, some expert demonstrations to show you how to do this. So instead of learning directly from, let's say, joint configurations like in kinesthetic teaching, we considered of actually learning cost functions, or as we call them, implicit priors, and use them for motion optimization. And in order to capture the multimodality in demonstrated data, we propose to use energy-based models, and I will give some more insights in a while. But generally speaking, these energy-based models can be used as implicit priors, basically to form cost functions, because they can capture multimodalities. They are composable because they belong in the exponential family. And they can be represented in any space, meaning that you can actually learn them on the task space and deploy differentiable forward kinematics to actually evaluate different, when you do basically trajectory optimization, to evaluate different robot configurations. So just a brief note about why do we call them implicit models, why they are better than explicit models. So our work was effectively inspired by these success stories that you see in image generation, where energy-based models and diffusion models have outperformed previous explicit models like variational autoencoders or generative adversarial networks, because these ones tend to collapse into some modes, or they don't represent well the multimodality in the data because of the priors that we use. So we realized that the past works on learning from demonstration for motion optimization were based on explicit methods, like you have some distribution that you probably learned from somewhere, you sample some data, and then you have your own design cost functions, and basically you try to evaluate these initial, for example, samples. So our goal was to investigate whether we can use implicit methods in motion optimization, and we showed several, let's say, training advances that you have to do in order to use it for motion optimization. I don't know if I need to go to many details. Effectively, you can see that basically an energy-based models contains this term here that is called the energy, that it is a unnormalized density, that in order to become a distribution, it requires to be normalized. And usually this is painful and requires Monte Carlo integration. Now, usually how we train EBMs is basically using contrastive divergence, that is some sort of maximum likelihood estimation. You try to push positive and negative samples in order to create positive and negative energy landscapes. And usually this is a bit too strict. It creates some sharp, let's say, edges in your energy landscape. Now, if we look at the motion optimization approach, we have usually some, for example, prior over trajectories and possible contexts. The context could be, for example, possible goal location or some target, for example, liquid, mass liquid that you have to pour. And effectively, we can see that these priors that you may have can be composed into factors, especially if they consider to be independent. Now, if we take a planning as inference approach, so we have to do a probabilistic perspective, we can effectively form motion optimization as a maximum a posteriori problem. And we can see here the duality between planning optimization and inference, where while in the planning, we need to evaluate with respect to some cost functions. When we consider our energy-based models, basically we have to evaluate with respect to some energies. And overall, our goal is to find optimal trajectories that minimize the sum of some costs that maybe you have hand designed, for example, smoothness in your trajectories, plus some energy that you've learned from some demonstrations, and consider some context, like as I said, pouring some quantity. And effectively, we can see the difference of having an explicit prior that samples some trajectories and evaluates them, as I said before, to some cost, compared to have, again, some samples. They can also come from learned initial distributions, but effectively you evaluate them from a composition of learned and hand-designed cost functions. So yeah, the explicit priors are not composable. They have limited expressivity, and they are usually learned in configuration spaces, while the implicit priors as energy-based models are composable because they belong in the exponential family. And you can imagine that, for example, distance-based costs can effectively be considered as Mahalanobis distances in Gaussian, so they can be composed with energy-based models. They are highly expressive, and you can learn them in the task space, as I said before. So we introduced several advances on how you can train these energy-based models to use them for motion optimization. I am not going to say all the details, so please look at the paper, but in essence, we create object-centric representations. We produce basically, this shows basically the object-centric kind of approach, where we can move the, let's say, this ball for the pouring, and the agent will actually follow up. We can have phase conditioning when we are talking about trajectories that are time dependent. So we can discretize the steps and actually learn phase conditioned EBMs, especially for the pouring task, but we can consider also other tasks like, I don't know, handovers that have some specific timing. And effectively, we can do denoising score matching. I will talk a bit more about this in a while, but this gives us smoother gradients. We're learning that it is effectively important when we are doing planning like GPMP. And we have also shown that you can integrate also other priors as initialization for your trajectories. And we've shown that in a toy experiment, we can see some initial demonstration from some random planner for different configurations of obstacles, where we can learn our cost over these trajectories, introduce some additional prior, and have these smooth trajectories over different goals, compared to behavioral cloning that you can see collapses to a kind of mean, let's say, behavior. And we can effectively also showcase this pouring task on the robot, where we learned initially from demonstrations. And by adding our costs for obstacle avoidance, that in this case, they are not learned, but you could consider learning also the costs for obstacle avoidance, we can realize the pouring regardless of how the scene looks, right? And as I said before, the notion of diffusion now, I don't know if you follow like the new RIPS updates and so on, like you will see diffusion models playing around everywhere. Diffusion models are a way of learning some models to generate samples by iteratively moving noisy random samples towards a learned distribution. So it's very interesting because basically you induce a lot of noise on different levels when you are deploying diffusion models. And a common way of training energy-based models with diffusion is by denoising score matching, where we first perturb some initial distribution with some Gaussian noise on different scales in order to perturb this initial distribution. And in order to sample from this distribution in practice, we first sample data from our original distribution, and then we add some random noise according to the scale of our Gaussian noise. And we can estimate the score function of this noise perturbed distribution by training a noise conditioned EBM by score matching. So basically, effectively, you only care about the energy component. So only the score, only the likelihood component of your energy-based model. And okay, some details about the training loss, that it is different from the original way of training energy-based models. And this is very favorable because it gives you directly the derivative of the energy function. And in order to do inference, you have to do annealed MCMC with an inverse diffusion process. So you effectively, I will show you in a while how this is realized in SE3 for robotics. So while diffusion has been demonstrated in images, we have seen it playing out amazingly in generating realistic images, it is in 2D space. On the image space. So we wanted to bring diffusion into SE3, so to train EBMs in complex SE3 distributions. And for that, we introduced SE3 diffusion fields. That is a scalar field that provides effectively, basically an energy, a value for any arbitrary point that lives in SE3 and some noise level. Okay, so we learned this energy-based model with denoising score matching as a test bed of a difficult task of learning, let's say, a distribution. We consider the task of grasping, of 60 grasping, because 60 grasping is effectively an open problem. Usually, standard approaches would learn a variational autoencoder, for example, and sample some initial grasps. Then you deploy planning and you say, okay, this grasp was good, I will execute it. However, by training with this process, I will not go through all the details. I don't want to put too much information and too much math right now in your mind, but effectively, we deploy Lie algebras in order to realize the derivation of the gradients in SE3, such that we can effectively follow the process of training by diffusion, and in order to sample with MCMC Langevin dynamics. And this is very important because since we are deploying stochastic Langevin dynamics, we only need the gradient of the energy, and we don't need to effectively integrate in order to normalize our distribution. And here is how the inference looks like. So you start from the inverse process, as we said, the inverse diffusion. You start from a very noisy, highly noisy distribution, and you effectively collapse to the lowest level of noise that basically belongs to the convergence to the actual distribution, your original distribution. And here are some random samples that we have, that we showcase. In theory, you can sample many more samples. Of course, you have to parallelize. Luckily, we are using neural networks, so this is feasible. This is how the neural network looks like. Internally, we are also learning the SDF of the object, because we found that it is actually useful to take the features from learning the actual, let's say, manifold of the object, and then around the manifold represent the manifold of the actual grasps. And what is important now to note is that by having access to this gradient of the energy, we can effectively use it as a cost function together again with other differentiable costs as before, and do grasp and motion optimization in a single optimization pipeline. And effectively, this allows us, for example, to do just, let's say, collision-free grasps. I don't know why this is not playing. Okay. For example, here as I said, we compose this objective together with obstacle avoidance objectives, such that the agent is able to just grasp the mags and lift them to a respective configuration. But we can also effectively solve problems of pick and placing, which means that the optimization process is able to select the grasp that it is the best for realizing a placing, especially when we also consider confined environments like this shelf environment that can be considered, let's say, a narrow environment. And you can see that the agent selects a grasp that would allow it to place the mag in an upward direction on the shelf, regardless of how we place the mag or how we change the scene there. So yeah, I am approaching to closing the talk. Sorry that it takes a bit longer. But if you are tired, I can also stop. But I would like to ask if there is any question like at the top of your mind right now. Feel free to ask anything. I don't know if anyone has any question. If not, I will finish up with the important topic of safety, and we take a learning perspective on safety. First of all, we wanted to be able to learn some constraints, in particular when we are talking about self-collision avoidance, when we are doing whole body control, or when we are doing human-robot interaction, being able to query efficiently and very fast collision points with the other agent, it's very, very important. And while we know that we can deploy signed distance field to actually represent such collision avoidance objectives, it is actually quite computationally expensive to do this in the real world, or it is not very fine-tuned because, I don't know, we use voxelized versions of our objects and so on. So what we have considered in this case is to take the idea from deep SDF, so the approaches that they learn design distance fields of objects with deep learning, and extend them for articulated objects like the robot in this case. And also inspired by, let's say, Euclidean SDFs, we want also to be able to adapt these distance fields at arbitrary scales according to different applications that we may need to do. For that, apart from the fact that we consider the pose of the articulated object as an input and not only a point that we try to understand whether or not it belongs on a manifold, but also it is subject to the actual pose of the configuration of the robot in this case. We added a trainable regularization in the sense of realizing the object, in this particular case, again, the robot, as a point mass whenever we are very far away from the actual manifold surface of the object, and then push it down and take the shape of the manifold whenever we are approaching closer to the object of interest. And this requires some trainable parameters that actually gives us this smooth transition, and I will show you in a while how this looks like in real world deployment. Effectively, we are able, with this regularization, to approximate pretty well very complex manifolds also in any possible configuration. And you can see here, for example, for the human manifold, our approach compared to the deep SDF and the other competitive approaches, how much smoother are the level sets of our SDFs, and how we can effectively also learn very nice, let's say, refined manifold for our articulated object. Here it's a human, and here you can see how effectively, as the robot approaches the human, the manifold scaled from a ball into collapsing into the actual manifold of the human. And of course, this is not enough. We have shown here that in this paper that we can use these learned SDFs to effectively query very fast for collision avoidance when we do standard operational space control, but we want to learn complex interactions with humans, and we want to be safe. And for that, we need to always take care of our constraints. So for that, we consider reinforcement learning problem where we want to learn some task, we want to maximize our expected return subject to some constraints, either learned or again, human specified constraints. And if we consider the, let's say, the generalized coordinates, there are some part of the robotic state that are controllable, some part that it is uncontrollable. We can effectively consider the manifold of the constraints. We can assume that the constraints that we consider are both equality and inequality constraints. Therefore, we can also introduce a slack variable into our problem. And basically, you can consider that this is also inspired by operational space control and null space control. By considering the constraint manifold, we can actually take the tangent space of our manifold by taking the null space of our Jacobian of the constraints. And we can now alter our original action space into an action space that is required to always follow the tangent of the constraint manifold. And in this case, we always ensure that we locally do not violate the constraints. And how can we use this? We can actually use this approach to learn challenging tasks like differential drive navigation, where here we consider the differential drive constraint along with an additional constraint on obstacle avoidance with some SDF on this random agent and collision with these walls. And I will replay it back. You can see that the agent is able to reach the red goal, avoiding the agent and still complying to the constraints of the environment and of its system. And we can use our learned constraints to effectively learn dynamic manipulation in this shelf, again, bookshelf environment, and transfer it into the real world without much loss of, let's say, sim to real gap performance. And effectively, we can also deploy it with a human in the loop. Here, the task for the robot to deliver this glass upwards towards the human. The human was instructed to not take into account the robot, pretend that the robot is not there, read the phone, and reach out to take the orange there. And as we can see, the robot is able to react to the human to guarantee safety with the human, with itself, with the table, and keeping upwards, so the constraint of the task that was to deliver the glass upwards. So yeah, this was my story today about how we can use effectively structure in different components for learning scalable robot behaviors. We have seen this in different scenarios, but my vision is to effectively combine all this together for mobile manipulation tasks to be realized in the real world. My takeaway message, if I am allowed, is that we should remember that we are standing on the shoulders of giants. So there has been so much work before us. So we have to use it and combine machine learning with classical robotics. We need to use the structure of the problem because this is the way to scale robotic behaviors. Overall, we are mostly working with structured robotic systems. So we need to put this inductive bias into our learning algorithms. When it comes to human-robot interaction, we need to take into account also the structure of the human itself and not just consider skeletons and stigmas and effectively learn safe human-robot interactions. And finally, I think that it is important that we put effort into learning mobile manipulation. There are so many open problems there, also in part of perception, because this is the way for embodied intelligence. So yeah, this was all from me. Thank you for your attention, and I am now open for your questions.
Thank you, Georgia. Very cool talk, a lot of interesting insights. Let's open the stage for questions. You can either raise your hand and I'll call you, or write in the chat and I will read the question for you. Let's see if we have some icebreaker. If not, I might go. Okay, I can go first. So actually, I was one thing. So it's not really my field, but one thing I wanted to understand is you tried. You showed at the beginning some work you did in your PhD when you were trying these things with real people. So those were patients or people actually needing the robot. Now, relating back to your cool slides where you have these 5 points that guided your talk, where do you think is the challenge? Of course, it has to be a mixture of those 5, but in which one of the 5 is the challenge to actually be able to give these services quickly to these people in the future?
I would argue that safety is the most important challenge right now. Safety and reactivity, basically, because I mean, you can be safe, but if you are not fast enough to react, to guarantee safety or to act proactively. So safety can be not hitting a human. Safety can also be acting proactively to assist a human because, for example, the human is unstable and may fall. Therefore, in this particular case, like the agent would have to position itself differently to support the human. We didn't go so far of having such scenarios because obviously you could not allow the people that participated in the studies to actually fall, but this was the overall objective. And I would say that it is partially the algorithms, but the other important part is the hardware. So the hardware has to allow you to be able to do control at high frequency, and also that you can have some sort of compliance. And this is, I think, a very important part. So yes, I would argue that this is the most important thing right now.
Okay, cool. Thank you. And out of curiosity, like your application sits between the classic autonomy, so you might have the same problems that, I don't know, an autonomous vehicle companies has to have with regulations and so on, but you also are close to medicine or these kind of things which are even stricter. I imagine like robot surgery and so on. Very practically, how long does it take for a robot to be approved, or what is the procedure if you want to use your robot in a real scenario these days?
For the domestic, let's say, environments, actually, we don't have the necessary framework right now. So most of the specifications come from the human-robot collaboration ISOs. But these are also the ones that you use for manufacturing domains and not exactly for like cobots, right? And not exactly for human-robot interaction at homes, where there are also ethical constraints, there it's more complicated. So I would say that right now we don't have still the necessary law framework to say that this is the process, which is problematic and should be at some point fixed.
Okay, I was suspecting this, but I
Yeah.
wanted to be sure. Very cool. Is there any other question? I don't see raised hands. No one? That was because the talk was very clear, and also probably
Yeah,
it's
it
getting,
could be that it was clear or not.
no, because also it's getting darker in Zurich, I guess in
Yes,
Darmstadt as
it's the
well.
same.
So
It's the
people is
same.
getting sleepy.
Of course. So anyways, like if anyone wants to reach out, like after the talk, like if you remember something or you find something interesting, you can email me or any of the co-authors, and yeah, feel free to reach out. We'll be happy to answer questions.
Oh, I think we got. Okay. So somebody is saying that he will reach out
Yeah.
to you. Actually, also I noticed that one of your co-authors studied with me, Niklas Funk. I think we did the
Yeah.
masters together.
Great. Yeah, Nicholas is amazing.
Very good. Say hi from my side.
I will tell you.
All right, Georgia, thank you very much again for the great talk. I
Thank you
will
all.
keep you posted with the link of the video once it's uploaded, and
Sure.
all the best for the next
All
steps.
the best to you and also to the rest of the team.
Thank you.
Bye
Bye
bye.
bye. Take care.
Take care.